சரி பண்ணி இல்ல டேட் தெரியாம இருக்குது இந்த இடத்துல பண்ணுறீங்களா
So hi everyone, maybe we'll wait for a minute or two and then we'll start. Is there any doubt for those who are raising their hands? Okay, so I think we can start now. Maybe when more people will join, I'll admit them as the lecture goes on. So welcome everyone to the live session for the course of Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Jodhpur, and for this particular course, I'll be assisting in solving some of the similar assignment problems that have been given to you in your assignments related to each of the week. So for today, we'll be starting with the week one content, and as the course name suggests, this will involve learning about the semiconductor device modeling, which is a very good aspect for the individuals who are very reluctant to pursue research. So it would be great if you all can attend this lecture regularly because it will give you a very great insights about what is going on in the semiconductor industry and what exactly is modeling and simulation and why is it very necessary for us to actually even do the modeling aspect. So with that, let's see the course outline. As you can see, the course outline is basically, I mean, if I pertain to, let's say, week one, it is only about the introduction or the silicon-based. Yeah, so it is more or less related to the introduction about the nanoelectronics. So I'll let you know why the term, why do we call it nanoelectronics and not microelectronics now. Then device scaling, I'll let you know what is the basic of device scaling. Then we have certain different structures that are coming into the state of the art that are present in your mobile phones, etc. So we'll be having very basic insights about this heterostructure and nanostructure, and then some of the few basic topics that will start in this particular week will be the crystal structure, unit cells, and the Miller indices. So since we have low number of students only, so maybe if possible, could you kindly introduce yourself? You can just tell your name and your affiliation and what you are pursuing, if it is fine with you. Lingesh and Kisavan. I hope I'm audible, right? Could you confirm if I'm audible? Hello. Could you please confirm if I'm audible? Okay, so I'm assuming I'm audible correctly. And okay, so let me start with a very basic overview of, as a course name suggests, semiconductor device modeling and simulation. So we'll be initially understanding about what exactly this particular word means. What is device modeling? So let me start. with a very basic overview of what is device, sorry, modeling. So, has anyone heard this word before? If not, so you might have seen that what we do is we have a silicon in abundance in our nature, and what we do is we fabricate different devices. That is the very basic of what we do. So, we have silicon wafers that, let's say, which are having certain diameter. Let's say 2-inch wafers, we have 2-inch, we have so on, and we have till 12-inch wafers. And what do we do is we fabricate different devices on these wafers using certain processes that are not included in this course, but that is what we call as the fabrication of a silicon device. Now, this is just fabricating. So, I mean, what we can do is we do a lot of device simulations in terms of TCAD, like we design a device even before fabricating it. And why do we do it? Because we want to save a lot of resources. So what do we have? We have at one side, what do we have? We have device design, and at the second side, what do we have? We have circuit simulations. So to perform circuit simulation on these different kinds of devices, even that are made by foundries, so to bridge these two together is what we require as a compact model. And compact model in very basic terms is nothing but mathematical representation. And it is a mathematical representation, or it has mathematical equations, which is, let's say we have a very basic device. Let me start with the MOSFET. Let's say we have a MOSFET, N-type MOSFET, which has a P substrate. We know this is the source, this is the drain. We have a, let's say, a oxide, and then we have a gate, and we have also a body in a MOSFET. So in very basic terms, what can I say? I can say that the current or charge of this device as a function of this terminal voltages, whether it's gate, whether it's drain, whether it's source, or whether it's body. This equation or the representation of these is nothing but a compact model. So what do we have? Now we can see that we have these types of relations. So with these relation comes into the picture the parameters. So we have certain parameters that are involved in a compact model, and why do we use this parameter? We use the compact model to replicate the device behavior. So this is why we in particular need any compact model. Why? Because we don't want to just fabricate the device, but we also want to save a lot of resources. So this is a very basic overview of what is a compact model, or what is do we call a semiconductor device modeling. And as I said, in in this particular course, we will have different types of, let's say we are designing a device not only in foundries, but let's say we are designing a device in a environment which is technologically computer aided design, and we try to have now the circuit simulation. So to have this simulation, we need to have compact model for us, because this is the compact model that is basically replicating the device behavior, and it will let us know about the device behavior just by simulating it. So what will happen by doing that? It will save a lot of resources. We don't just want to fabricate the wafer directly and check every time whether the wafer is working like that or not. So that is why a compact model is a necessity in any of the industry relevant domain. So is there any doubt in what a compact model is? Anyone? Let me give a very basic example too. So you must, as I said, this is nothing but kind of equation. So you must have, I mean, in your class 10, 11, you must have read this diode, which have a certain IV, which is exponential in nature, And we have a very basic equation of diode, which is I is I naught exponential of something V naught by eta kt minus 1. So this is nothing but, so this equation, the making of this equation is nothing but the process is called as modeling. Similarly, even, I mean, let's say you must have read in your BTech or PSC, whatever you are pursuing currently. So let's say we have a MOSFET and this is the gate and this is the oxide, this is the gate. So you must have read about the current equation, which is nothing but mu and Cox W by L. Let's say I'm talking about saturation, it's nothing but VGS minus VTH whole square. Right? So this equation has come out from where we have done some modeling of the MOSFET to replicate the IDVG or the IDVD of a MOSFET. We have made out this equation. So now you see these equations have different parameters, as I said. So this is the mobility parameter. This is the oxide capacitance parameter. This is the width, length. So length and width, we know that width is in this direction. And this is the length, which is also called as the gate length for a MOSFET. And then what do we have? We have the application of gate to source voltage. We have the threshold voltage. So these equations that we are making is kind of what we are doing as a part of modeling. And this is not as simple as it looks. So we know that as the device scaling is happening, we have a lot of unreliable, or not unreliable, but undesirable effects that are coming into the picture, which we call as the short channel effects. So has anyone heard about short channel effects? Any idea, guys? Actually, I would encourage you to be interactive in this course, because this course is actually very interesting, and it will help you in finding jobs quite easily in related to the research areas. You can even pursue in this particular you can even pursue PhD in this particular domain, because in fact my domain during my PhD is related to this course only. So I would highly encourage you to be interactive, and if you have any doubts at any time, please open your mic and let me know about your doubts. I'll try to solve them as much as I can. So as I said, I was asking that has anyone heard about the short channel effects in some of the course that they might have read in their BTech MTechs? Okay, so let me give you a very basic overview of what short channel effects or what device scaling is. So, because this is one of the topic that is being given in this particular lecture. So let's say we have this MOSFET, which is N plus N plus at this side, and we know that this is nothing but the channel length, right? So we have this channel length, and what are we doing is, as I wrote the formula, mu1 CXW while something something, let's say. So if what will happen if I reduce the length, what is the ultimate output that we want? We want higher and higher current from any device, because that is the ultimate goal of any semiconductor device. We want more and more current out of it. So what we have been doing from several decades is we are trying to reduce this channel length of any of the device. By that, reducing the denominator, we are trying to increase the current, right? So what I think you must have heard a name which is called as the Moore's law. So which says in every 18 months, what happens? The transistor doubles, right? If I talk about same area. So let's say we have a 1 cross 1 box. Let's say it has one transistor for this year. After 18 months, it will have two transistors. That is the density of the transistor is increasing every 18 months, right? So this is what we call as the Moore's law. And this happens by decreasing this, right? So if let's say if I even decrease this channel length even smaller, let's say this is the source, this is the drain, and this is the length now. So by reducing this length is what we call as device scaling, right? So what do we have? As this comes into the picture, we know that we can have the conduction directly even after even not even applying about the gate voltage, right? So what do we have? We have several leakage currents that are coming into the picture. So these are undesirable, right? We do not want any leakage or anything undesirable that happens to our device. So this comes into the picture, which is related to as the short channel effects. So we'll be discussing the short channel effects in this course in maybe the last part of the section, sorry, last section of this course. But I'm just trying to give you an idea of about what is device scaling and why do we even need it, because we want to have more and more currents. So you must have, I mean, you must have your phones with you. So in your phones currently we have technologies which is called as FinFET. Then we have a technology which is also known as nanosheet. So if you have heard, so in iPhone, let's say 17, so what do we have? I think the current iPhone is 16 or 17. They had 3 nanometer, you must have heard if you are technologically geek. They have 3 nanometer FinFETs. And for the first time in iPhone 18, they are introducing 2 nanometer nanosheets. So nanosheets and FinFET. So we are talking about a MOSFET as of now, right? That let's say we have a source, we have a drain, and then we have a gate oxide. So this gate is actually only one-sided, but to have a higher current, what do? They have a 3D structure which is having gate which is basically covered by metal on all the three sides. So it is now controlled on the three sides. So that is what we call as tri-gate MOSFET. So this was the idea that was proposed by Professor Chen Hu, and this is the discovery. This leads to a discovery of FinFET, and this happened around 2011. And it is still dominant in most of the mobile phones that we are using. So in iPhone currently that it is running by billions of transistors, and those billions of transistors are nothing but FinFETs. And in their upcoming technology, they are introducing for the first time as nanosheets. So nanosheets, we have metal at all the four sides. So more the control over the gate, more will be the stability and lesser will be the leakage in any device. So all of this has been done just to have a better control over the device. So now the point is, if we are going towards 3 nanometer node or 2 nanometer node, that means this difference is it will be at minimum 3 nanometers. So 3 nanometers is exactly not the channel length, but the minimum difference. So a 3 nanometer node can have a gate length of let's say 5 nanometer or even up to 10 nanometer. So now the my point is, let's say if we know that we have any atom, can anyone tell what is a average value of any atomic radius of any atom? Any idea? Like any order you might want to take a guess. Anyone? Okay, so it's nothing but it is in few angstroms. Let's say even if I talk about 1 to 10 angstrom, and that is approximately equals to 1 nanometer. So we do have carriers in the channel which is in the order of, you might have heard the doping is in order of 10 per 17 per centimeter cube or something. Now you try to imagine that we have a channel of only 3 nanometer. So what will it contain? It will only contain three atoms, right? So this is, I mean, the bottleneck of any device. So because of this, we cannot have more and more carriers into the device. We even try to increase the width, but that is also undesirable at certain extent. So what do we have is what do I want to try? What I'm trying to say is that we are reached to an extent that only this device scaling is not possible as it was going before. So now what people are trying is people are trying new materials. So by new materials, what do I mean by new materials? So we have this formula, right? It has a Cox, which is epsilon ox by Tox. So if we increase this oxide capacitance, if we use a high gate dielectric, this current will also increase. So people are trying to have, first of all, this terms. Now you might be able to understand now why do we call it nanoelectronics, because now we have the devices which are having the channel length or their technology node which is in few nanometers. So that is why we have went from micro to nano now. So this was the meaning of nanoelectronics, and the device scaling is kind of getting dead, but it is still relevant, but it is not as fast as it was used to before. And people are trying to have new materials such as, maybe I'll try to write There is a material which is called as HFO2, which is a high K dielectric that people are using for having a more and more current. Then the second material that we have is or are the 2D materials, which is nothing but MOS 2. Then you might have heard of WSE2, etc. People are trying to have different approaches. Not even the scaling is relevant as of now. People are trying to have different materials to have more and more amount of current. So this is a very basic overview of the introduction of what is nanoelectronics and what do we call as or what do we call as the device scaling. Now, if I try to say in terms of modeling, so this equation seems very simple. I think this has a very few parameters, but in reality, if I include the short channel effect, so that is what we call as a compact model, right? So we have several industry standard compact models. By industry standard, I mean that the industry is using it to validate the actual devices. So we have different groups that are present. So one of the group is called as BSIM, which is a Berkeley group, which is making compact models for different types of FETs, etc., and memories. Then we have a PSP group, which is Pennsylvania and the Philips group. Then we have HiSim group, etc. So we have a lot of groups that are trying to have the compact model. So in BCM, for example, we have a compact model which is called a CMG, which is a common multi-gate model that actually supports all the gate all-around FETs, which basically means FinFETs, nanosheets, etc. Right? Now this particular model, it looks simple, but it has thousands of lines of codes. And at the same time, it has thousands of parameters also that we need to have a complete knowledge of. Then it's so I hope now you are trying to relate that how difficult is it to actually make a compact model because it has thousands of lines, it has thousands of parameter, and every time a new fact comes into the picture any device, what do we have? We need to have that equation added in the existing compact model. So it is getting more and more complex as we go towards more and more complex devices, right? So what I'm trying to say, let's say if I make an IDVG, you might have seen this. So this is how IDVG looks like, not exactly this, sorry. And this is how IDVD looks like. So now maybe for very basic devices, this equation may be able to have solve this particular IDVD, but in reality, we have a lot of effects such as short channel effects, which includes Dibble, which includes subthreshold VTH roll-off, which includes charge sharing, etc. And that is why we have a requirement of thousands of parameters just to have the actual fitting or the actual replication of the device that is being made by any foundry. So this is a very basic overview of compact models and the importance of them and about the device scaling and the nanoelectronics. So is there any doubt in anything till now? If you're not able to speak, please type yes or no in the chat box. That is okay for me. At least a response somewhere. So do let me know. Maybe I can give you a minute or so. Do let me know if you are able to understand it or if you have any doubts. We'll wait for a minute. Okay. So I hope it is understood to everyone till now. So let's move ahead now. So maybe we can move towards certain questions. So as you have seen, all these devices, they are very, okay, wait, it is stuck somehow. Yeah. So all these devices that we even study are in general made of silicon, right? You might have heard of this word silicon. Every foundry guy knows that we are using silicon. So why are we using silicon? So the first question is actually similar to that. So the problem says the primary reason for the dominance of silicon in the semiconductor device technology is what? So maybe you can give your answers in the chat box as per your understanding, and then I'll also try to explain the same uh, as we go on. So we have one answer which is option A. So I'll wait for maybe some more answers, and then I'll try to explain the answer of this particular problem. So as it says, the primary reasons, we can have a lot of reasons as different options suggest, but the question is asking the primary reasons that we use for the dominance of silicon. Okay, so we have two answers as a. So okay, so the primary reason. So the first of all, the first option says abundance of silicon on the surface. So it is true that we have a lot of silicon on the surface. So anything that is what we call as sand, it can be converted into silicon. So we have abundance of silicon. That is actually true. Now the option B says it has excellent band gap property. So it is also true because silicon is actually very ideal having the band gap of in between a conductor and a insulator. So conductors, let's say this is ECEV, you should have known by now. So this is ECEV. So if you overlap this, this is a conductor which is highly conducting. If you have very far band gap, then it is what we call as insulator. And silicon has a band gap of in between, which is approximately 1.1 electron volt. So this is also true that it has excellent band gap. Now the third option says that it has favorable properties of SiO2. So actually this is the most important reason that we use silicon. So what happens is, let's say we have a sand, we have made it a silicon wafer. So let me try to make a wafer kind of thing. So if you just make this wafer in contact with any surroundings which has oxygen, so what happens? There is a grown oxide over it. And this SiO2 is a very good dielectric. As you have seen in any of the devices that I was making, we require a oxide layer just to have the control over the application of the voltage or the application of the current. So this is the most important property of the silicon, that once it comes into the contact of any oxygen, it grows a very uniform layer of SiO2 over it. So just by having a, what to say, the reaction between the oxygen and the silicon, we have a grown SiO2 over it, which is very uniform in nature. So we cannot have a very rough surface because that will not have very ideal current, or that will have very unrealistic effect. So we need to have a very smooth surface, right? So the most important reason of silicon dominance in the device technology is actually the growing of the SiO2 over the silicon. And the last option says lower melting point. So silicon has actually a very high melting point. That is why we use it. So D is incorrect, in fact. So the most, I would say the primary reason would be the favorable properties of SiO2. Yes, A and B are correct, but the primary or the most important reason is the properties of SiO2. So is there any doubt in this particular problem? Okay, so let's try to move ahead now. So maybe, yeah. So we'll move to very basic concepts now. So now the next problem says consider a free electron moving with a velocity of 138 of the speed of the light, and it is saying find the de Broglie wavelength, and C is given, the mass of electron is given. Okay, so maybe I'll try to tell the some of the basic effects. So semiconductor physics basically revolves around three basic effects. You might have already heard about them. One is the photoelectric effect, one is the wave particle duality, and last is the uncertainty principle. Does anyone have any idea about any of these? Have they been taught in the lectures taken by Professor Divek Dikshit? Okay, so let me try to explain one by one. So the photoelectric effect that we have, what does it say? That if we have, let's say, any semiconductor material, or even if we have any metal, so if we incident any light or any energy over it, let's say the having energy of h nu, then what will happen? There will be an injection or the electron will come out of it in form of light. So this is how the discovery of this photoelectric effect happened, and the energy is nothing but equivalent to h nu, and nu we know that it is a frequency which is also h c by lambda. So this is what the photoelectric effect is. What does it say? That if we incident any energy or if we incident any energy in any metal, there will be a injection of any, or the electron will come out of the metal if the energy that we are applying is greater than that the band gap of the electron, right? Because once we apply a certain energy that is greater than that of, let's say for example here, so let's say this is a valence band, and if we apply energy which is greater than that of 1.1 electron volt, this electron will come here from valence to the conduction band. So this happens in form of light is what is proposed in the photoelectric effect, and this is was given by Max Planck or Max Planck, whatever you call it. Then the second principle that we have is the wave duality principle. So and wave particle duality principle. So what does it says? That maybe I can write wave duality. So it says that let's say we have an electron, it can act both as a particle as well as a wave. So by particle, we know that particle can have any kinetic energy, potential energy, etc. And a wave can have, let's say, wavelength, right? Frequency, etc. So how can this both can happen? So it is given by nothing but the de Broglie wavelength, which is h by p, or which is what we call as h by mv. So this was a question that we refer to in the last slide. So we'll do that later. Maybe I can also explain the third principle, which is maybe I can give you an example of how can we say that it exhibits both particle and wave nature. So let me give you a very basic example. Maybe you can give your calculations also. So let's say we have an electron. We know that the charge of electron is 1.6 10 to the power minus 19 joule. Not joule, but coulomb. We know the mass of electron or the effective mass is 10 to the power minus 31 kg, right? And let's say any electron can move easily at maybe speed of 10 to the power 5 per second, which is close to speed of light but very less, 3 orders less. So if I try to calculate the wavelength of this electron, so as the de Broglie principle says, it is nothing but h by p, which is given by h upon mv. So if I try to put the Planck's constant, which is 6.626 minus 34, then I have 9.119. Then we have the mass, and then the velocity I've taken as 10 is per 5. So everything here is in centimeter. So the final wavelength that will come out to be should be in centimeter. Oh no, everything is in meter, sorry. So the wavelength that should come out should be in meter. So this should be minus 3, should be minus 9. Okay, so it should come out to be something 7 point something something 10 is per minus 9, which is approximately 7 nanometer. So we have a certain wavelength, right? So can we call electron as a particle? And it is behaving like a wave because it has a certain wavelength, which is in a particular order. 7 nanometer is actually a wavelength. And if I, at the same time, if I consider, let's say, an example of a tennis ball, let's say I'm taking a ball, we know that the cricket ball that we play with, let's say it has a mass of 50 grams or something, that is approximately zero point 0.5, not zero point 0.5, but 0.05 kg. And let's say we are throwing it because it cannot attain a very high velocity. And let's say the velocity is approximately 50 meter per second. Now, if I try to increase or try to have a wavelength, then it will be 6.626 minus 34 by mv. So mass is 0.05 and then velocity is this. So can anyone tell what will be the order of this particular thing? Around what will be the order that it will come out to be? So as it says, this is zero point 0.5 times 5, which is 2.5. This should be something around 4, but in the order of 10 to the power minus 34. So this is very, very low number, right? So it cannot act like a wave. Any big particle cannot be a wave. So hence electron, we know that electron has a kinetic and a potential energy, but it also has a certain amount of wavelength, right? So that is why we call it as a wave particle duality nature, which is given by de Broglie, and the wavelength of that is this. And the third principle that I just wrote was uncertainty principle, right? So it was given by Heisenberg. Let me write that too. Does anyone know what is Heisenberg uncertainty principle? Anyone? Okay. So what it says is we cannot determine both momentum as well as the position of any atom simultaneously. So either we can know momentum or position of any atom side by side. So that is why the whole semiconductor physics revolves around the probability of finding. You must have read about, I mean, I'm not sure if the course has covered that, but we have a Fermi function that we use, which is nothing but the probability of finding electron. Because there is nothing definitive in semiconductor physics, because we cannot have both position as well as the momentum known to us at any point of time, which is given by Heisenberg. And that is why we call it as an uncertainty principle. So, yeah, I mean, these are the three basic principles that we have read. So now the problem that was there, it said we have an electron having velocity this, wavelength we need to find, and everything else is given. So maybe I'll give you 2 minutes. Please try to write your answers in the chat box. This is a very easy problem. I've already given the formula or explained it. So take 2 minutes and let me know your answers in the chat box. Okay, so I've got one answer is D. Let's quickly calculate. I mean, this is quite easy. So C is given, so we know the wavelength is nothing but h by mv, right? So h is 6.626 times minus 34, sorry. Then we have mass, which is 9.11 minus 31. And the velocity is 1/30th of this. So 1/30th of this will be 10 raised to 7. This will be minus 3. So it will be something minus 9. Oh no. So this will be 9, 6, 7. So 7 point something minus 2. So it should be 7 point something times per minus 11 meter. Is there any option like that? Yeah. So option D is the correct answer. So yeah. Is there any doubt in this? This is a very straightforward problem. Please let me know if you have any doubt. So if not, let's move ahead. Okay, so we have a next problem which says let E1 and E2 be the energy of an electron in the first and second stages of an hydrogen atom. Oh, so for this, what do we need to know? We need to know about the very basics about the Bohr's postulate, right? You should have read those in your class 9th. So can you tell what are the Bohr's postulate? Anyone? I would request again, please try to keep this class interactive. It would be good because in the upcoming classes we have a lot of important topics. We know, well, I know this is very easy for you all to for now, but if you don't keep it interactive, it would be, I mean, it would not be beneficial for you because if you try to keep it interactive, we'll have more questions and we'll have more understanding of the concepts. So Bohr's postulate that we study, so we know that we have three postulates. The first postulate says that energy is not continuous or energy is not present everywhere, but it is present in discrete nature. So energy is discrete, is what the first postulate says, and we know that let's say this is a nucleus, so we have energy present at different levels or what we call as shell or bands. The second postulate at the same time says that if there is any atom which is going from one level to another, it is nothing but the frequency of that atom would be the change in energy times the Planck's constant. So this is the second postulate. The first postulate said that the energy is discrete in nature, but it is not continuous. And the third postulate, we know that it says that the angular momentum of the electron, which is nothing but mvr, it's again quantized, and it is a multiple of h upon 2 pi. So this is the third postulate, right? And if we try to calculate nth energy level, we know that we have a very famous formula which is minus 13.56 g square over n square, and this is in electron volt. And z is nothing but the atomic number, so it will be 1 for hydrogen, which is asked in the question. And n is the nth level of energy. So we have ground level, we have first level, and so on. So if I just try to make a diagram out of it, so let's say if I try to make a box, so the 0th level we know that, I mean, we cannot have, it is infinite. Now if I try to have 1, so if I keep 1, it will be nothing but minus 13.56, right? I'm talking about hydrogen only. If I keep 2, so it will be minus 13.56 by 4, so that is around 3.39. If I keep it, let's say 3, so it will be 1.51, right? It will be 3 square, that is 9 electron volt. And if I, let's say, keep it infinite, so it will be 0. So as you can see here, what do we have is, as we are moving away from nucleus, we have higher and higher energy. So this is what the basic discretization of energy means. And here the question is asked you to the change between, let's say we have E1 and E2, energy level of first and second stages. So what do we need to find? We need to find E2 minus E1. So you know that En is minus 13.56. So it is hydrogen. So okay. Let's write Z. So Z will be 1 for hydrogen, and N is equals to 2 and 1 in the question. And it is asking in joule. So this is actually in electron volts. So 1 electron volt is 1.632 joules. Oh, sorry. 10 minus joules. So I'll wait maybe again for 3 to 4 minutes, and I'd request everyone try to solve this problem and write your answers in the chat box. So I've got different answers. One is A and one is C. So let's check. So I think it was very straightforward. So just about the calculation. So let me try to calculate. So it says E2 minus E1. So if I try to write in electron volt, it will be minus 13.56 by 4 minus or plus 13.56 by 1. So this will be around, if I calculate, this should be 3.39. It should be approximately 10 point something, right? So if it is 3.39, so it should be 10 point something electron volt. And the question is asking in joules, so we need to multiply it by 1.6 into 10 to the power minus 19. This will be in joules. So the answer would be around 1.6 approximately 10 to the power minus 18, because we have a 10 electron volt. So that is option, yeah. So option A is the correct answer. So sorry, I was on mute. So as I was saying that we need to find that E2 minus E1, and I've done nothing but just put it in the formula. So we are getting around 10 electron volts, and 10 electron volts is nothing but 1.6 times 10 to the power minus 18 joules. Is there any doubt in this? So those who were getting option B or A, sorry, B or C, is it clear? Okay, that's great. So let's move ahead. As we know, this particular week we also have, I think, topic which is called as crystal structures and mirror indices. So let's try to cover that too in this particular lecture. So this lecture might be a bit shorter than as compared to the rest of the lectures, because this is just an introductory lecture. So let's keep it short. So okay. So now the next topic is crystal structures. So I am hoping that it is already being taught in the in the classes that have been taken by Professor Dikshit. So it says, this particular problem says we have a material X which is crystalline as lattice, diamond lattice. So lattice is nothing but the periodic arrangement of atoms, right? So we have, I mean, in the course that we have 3 to 4 arrangements. One is what we call as FCC, one is what we call as BCC, and the third is nothing but the diamond cubic, which is a structure of silicon. FCC is face-centered cubic, and BCC is body-centered cubic. So what do we mean by that is, let's say we are having a cube, a periodic arrangement, let's say in form of a cube. So face-centered, by face-centered, what do we mean is that it has atoms at every corner, first of all, which are 8 corners, right? So let me make it completely. So we'll have this. And face-centered. So at every face it has. So let me maybe have a face which is shaded like this, which is a front face. And if I try to have, it has an atom at the center of the face also. So at every face it has like that. So this is what we have, the FCC structure. Similarly, the body centered, what do we have? We have the atoms at all the corners and at the center of the body. So a complete atom at the center of the body. So if I try to, maybe I have an example. No, for now I am not. And in the diamond lattice, what do we have? We have arrangement like this. So we have atoms at all the corners. Then we have atoms at all the faces also. And then we have 4 atoms in the middle of the body also. Right? So, okay, so is this and this question same? Yeah. So this is actually the complete problem. It says, yeah, we need to calculate the density of X, and this is actually the structure. And this is what we call as the diamond lattice, and this is what the silicon is made up of. So for this particular type of problem, there are particular steps that are required, that we require to follow. So the step one would be, we need to find number of atoms in the cell. Number of atoms per unit cell. So we have atoms at all the corners. So we have 8 corners, right? And what will be the contribution? So can anyone tell how many cubes uh, can we have adjacent to all the corners? Any guess? This is a very easy problem. I mean, just try to think that, let's say we have a cube. How many cubes can we have around that particular corner? So if you think about it, let's say we have a cube here also. We have a cube there also. We have a cube there also. We have a cube upper also. So this corner can have, any idea from this picture now? So there will be 4 on top, there will be 2 adjacent, there will be 1 on the side. So it will be how many? Anyone? Please try to be interactive and think about it and let me know your answer in the chat box, please. So we can have 8 cubes at the center. So 1/8 will be present at every atom cell. So let me ask a easy one then. Since we have all the face centered. So let's say this is one face side, right? Let's say I'm taking this face and there is an atom at the center of it, which is this atom. So what is the contribution of the face atom? Can anyone tell? See, this is very easy now. Think about it. Let me know. So what amount of the atom will be in one cube or one phase. Come on, everyone. Try to have a guess already. Two. Yeah, so that is good. So we can have an atom. So half of that would be here and half of that would be there. So at every phase, let's say we have an atom. So we have six phases. The contribution would be half. Then in the diamond cubic, we have four atoms in between the body. So it will be 4 into 1. So the number of atoms per unit cell for this will be 1 plus 3 plus 4. It would be 8. So this is the step 1 for each and every problem that we are that will be solving for the crystal structures. Then the second thing that we calculate is the mass of single atom. It will be nothing but the atomic mass. So this is a standard formula divided by Avogadro number. So this is always given in the question and you can also remember the value of it. And atomic mass, right? Atomic mass also is well known in the question itself. Is there any doubt? Yeah. And then at the last, we'll calculate the density, which is nothing but atoms per unit cell that we have calculated. Sorry. Multiplied by the mass of one atom. So this should be in grams. This is the number divided by. So what should be the denominator? What is the density? Density is mass per unit. Anyone? What should I write in the denominator? Density is nothing but mass per unit volume, right? And we know the volume, let's say we have a cube, so the volume would be nothing but a cube if the side of the cube is a. So we have everything now, we just need to we need to do some calculations. So let's do that. Atoms per unit cell is 8 for this. Mass of one atom is 30 divided by the Avogadro number, which is 6.023 times 10 to the power 23, if I'm not wrong. Yeah. And then a cube. A is nothing but this. A is So for diamond lattice, we have a which is given as zero point 0.6 nanometer. So we need to see that what is the density that we are calculating in. So we need to calculate in centimeter cube. The question has asked in centimeter cube. So zero point 0.7 nanometer is nothing but zero point 0.7 times 10 to the power minus 7 centimeter, right? So the cube of this will be the final number. So 0.6 times 10 to the power minus 7 cube. So whatever this number comes out to be will be your density. So can you calculate quickly and let me know what is the final answer? So yeah, options are these 130, 3.8, 1.84, 18.4. So maybe you can take 2-3 minutes, have user calculators quickly and let me know what you are getting. So do we approximately Is that even calculated till yet? Okay, so I've got one answer which is B. Okay, let me see. So what I'm getting is this is 400 approximately. I mean, I'm not done the exact calculation. If I do it, it is approximately 1.8. Is it option B? Okay, so someone else is also getting option B. Yeah, so I'm assuming option B is the correct answer. You can recheck the calculations again if it is not, but as per my calculations, I'm getting the answer around 1.8 something something, so should be 4. Is this question clear to everyone? So I'll repeat the steps again. So in any question, we'll first find out the number of atoms per unit cell. Then we'll find out, so this is step 2. We'll find out the mass of single atom. And step 3, we'll find out the density, which is given by atoms per unit cell that we calculated in step 1. Mass of one atom that we calculated in step 2 divided by the volume, which is A cube. So A can have different values depending upon the different types of structures. So for example, in the diamond lattice, we have A as 3 root 3 by 8 r, where r is the radius of the atom. For BCC, I think we have A as 2 r, and for FCC, oh sorry, I think I've done something wrong. Yeah, so we have actually r as root 3 by 8a, and here also. So for example, let's say if I talk about body center, let's do a calculation for body center, because the next problem is related to body center only. So this is the next problem. It says we have a BCC structure. So BCC, I think I have a picture. So this is BCC, right? So as I said, this is A, right? And this is the center. So you can clearly see this is R and this is R, right? And if I try to calculate from here to here the diagonal distance of the cube, we know that this is A, this is A, this is A. So this comes out to be root 3A. This is the basic mathematics that we have read. And from the center, we have R plus R, right? So root 3A is equals to 4R. So here A would be, or R would be root 3 by 4A. Is it clear to everyone? Please let me know if there is any doubt. Is there any doubt in this? How we have calculated the A or R? So if you don't have any doubt, so the question is straightforward now. It says it has a BCC structure, so you need to calculate the number of atoms per unit cell. Then you need to calculate the mass per unit cell, so it is already given the mass. Then you need to find out the atomic concentration. So concentration is nothing but per centimeter cube. Then you need to find out the lattice parameter. You need to find out A as well as the R. So once you find out A, the R can be found out using this. Is it clear the question? How will you do it? Kindly write yes or no in the chat box if the question is clear. So if it is clear, try to find out the atomic concentration, the lattice parameter, and the radius. So this is again very straightforward. So maybe take 2-3 minutes and let me know your answers in the chat box. Okay, so let me try to do the solution. So as I said, the step 1 is number of atoms per unit cell. So we have for the BCC, we have 8 at the corners, contribution is 1/8, and we have 1 at the body, which is completely in the body. So it will be 1 plus 1, which is 2. Then mass of single atom, which is given in the question, I think, which is 95.94 by Avogadro number. So now the third thing that we calculate is density, which is number of atoms per unit cell, which is 2 multiplied by this thing, mass of single atom, which is this. So let me write something like this, divided by A cube. So this is gram per centimeter cube, right? So mass, if we leave this, this is nothing but the concentration. So this is what we need to find. Since the density is already given, which is, what is the density? 10.22. So this is actually equals to 10.22. So you know everything, we just need to find out this concentration. So from this you can easily find out A first, then R, and then concentration. So let me find out using some calculations. So 2 by A cube will be 10 by this thing. Ten point two two 95.94 6.023. So if we calculate A, it should come out to be not A cube, it should come out to be, I'm trying to write final answer, so it should be around 3.147 minus 10 meter. Then you can easily find out the concentration, which is 2 by A cube, which is 2 by this number cube. It will come out to be something, and similarly you can find out R, which is root 3 by 4A, which is root 3 into 3.147 by 4 divided by 10⁻⁻10 meter. So if I try to see A, I find out as 3.47, which is this, and okay, so 3 approximately this will be 0.9, so it should be 1.6 something. Yeah, there is only one option which is 1 point something, so option A should be the correct answer. Is there any doubt how we have done this problem? Anyone having any doubt? Please type in the chat box quickly, otherwise we'll move ahead. Okay, so let's move ahead to the last topic of this particular week, which is nothing but Miller indices. So Miller indices is actually just like a way of representation of any lattice or any crystal structure that is periodic in nature. So it says determine the Miller indices for the following planes. So let me give you the very basic steps of finding out the Miller indices. How do we do it? And then you can also try it out. So what do we do? So the step one of finding the Miller indices is you need to check the intercepts for each of the axes. Step two is write the intercepts in terms of A. For example, here, let's say in figure A. So what we'll do in figure A, we have X, Y, Z. So X is nothing but 2A, Y is nothing but A, Z is nothing but 2A. So now it's the second step was write in terms of A. So it is already written in terms of A. So it is nothing but 2A, comma A, comma 2A. Now step 3 is invert the intercepts or do the reciprocal. So this will become 1 by 2. I'm not writing A, 1 by 1, that means 1, and 1 by 2. The step 4 or the last step would be make it integer. So you need to multiply it by any number that will make all of these as integers. So if I multiply it by 2, so it will be 1, 2, 1. So this is nothing but the Miller index. Is there any doubt on how to calculate the Miller indices in any of the step? Quickly write yes or no in the chat box. So for A, the Miller indices would be 1 to 1. Also, we have two options. So we also need to find out for B. So quickly find out the Miller indices for B and let me know the answers in the chat box. So one thing is if there is no intercept in any of the axes, you need to take it infinity because it is not intercepting, so it should go towards infinity. Quickly write the answer in the chat box now. Which option is correct? It should be either A or D. So what one answer is D. So let's quickly write x is infinity, y is a, z is a. So second step is to write in terms of a. The third is invert. So 1 by infinity should be 0, 1, 1. Make it integer. So it's already integer. So it should be 0, 1, 1. So the correct answer is option A. Is there any doubt in this? Please let me know if there is any doubt in this particular problem. Okay. So if not, maybe I'll give one problem for homework. So this you can write and we can, when we meet next week at the same time, you can let me know your answer. So it says it has a silicon which a lead is constant. So A is given. Hard sphere model is again diamond cubic only. So you need to calculate the radius. So radius, we have already known that it is nothing but root 3 by 8a, and the density of the silicon. So again the same process that you need to find out atoms per unit cell, then mass of uh, atomic mass of each atom, and then finally the density. So you can take a screenshot of it, or you can take a picture of it and let me know your answers in the upcoming week, or you can mail me anytime. So let me tell those things too. So this is my mail ID. So if you have any concern regarding any of the problem in any of the week, you can reach out to me anytime. And you can also search my YouTube channel. So these recordings will be uploaded regularly on the YouTube channel. So you can maybe search Anant Singhal NPTEL and it might come up. So this is the mail ID, and this is yeah, this you can search on YouTube. My channel will come up. So I'll upload this YouTube video maybe shortly on the same day of the lecture. So this I'll upload maybe in an hour or so, and you can also see it in the YouTube recordings. And at last, we can have a WhatsApp group. So maybe any one of you can share the link to me in the chat box, and rest of them can join it, and I'll also join the same. So these three can be the way of communication between the lectures during the whole course. So if you have any doubts, quickly you can ask me. Otherwise, we can wrap up this lecture. Let me stop the recording.